the course helped me to understand how digital designs are produced in industry. Oh, if you're interested in electronics, take this course. I mean, it's an amazing course.
So let's get started then. Nice to talk to you, Andrey. Tell us a little bit about yourself and your background.
My background is physics. So I have like PhD in physics, was working on some accelerators early on, like in Max Planck for nuclear physics. Did some projects at CERN in Geneva, then moved to private sector from academia area and worked in a Dutch company which produces also accelerator-based things, including ion implanters for semiconductor industry. But since semiconductors became smaller and smaller, they needed less and less acceleration from accelerators. So it's like logic from the 80s probably needed deep implantation, which requires big machines. But when logic became smaller and smaller, that became kind of obsolete. So it is only now used, this kind of technology, for power electronics, where you still need to implant stuff kind of deep inside. Or sometimes what people are doing with them with some kind of defect engineering, that after you turn off your switch, it kills the charge carriers in there on those defects. And these defects were introduced by bombarding the wafers with hydrogen, so protons, deep enough so they were creating some dislocations in the material, etc. So like a bunch of these machines still works at Infineon sites in Europe, Villach and Dresden. And there were some other applications of these things. And for the last 3 years, I've been working in a quantum startup in Germany. It's called Electron with Q, because it's quantum, so it should be with Q. And in there, the key technology is the trapped ion quantum computers. So this is the technology where now we do it with kind of chips, but the chip in there is a little bit misleading. Like, in normal chips, the interesting stuff happens inside of the material. Like, you transfer charges from one place to another. You do something about this. And the chips which are used in trapped ion quantum computing, the interesting stuff happens above the chip. So your chip creates like a field structure in the open space, and there, like 100 microns above the surface, you have some ions floating in there, and you heat them with lasers. In our case, you also heat them with microwaves, and again, in our case, you also apply some magnetic field in there. So the chip is kind of more like antenna structure or so, but the interesting stuff happens above that in the free space. In that regard, that's like a radio tube. Only instead of a big stream of charged particles, you have like a handful of them, like 1, 5, 10. The most successful company has like 54 or so, 56. And this was actually the thing which led me to the course, because I started to deal with those chips and how we kind of supposed to do them. And then there were a couple of things. One is like a very low level, so we kind of design our chips, but not that we have like a PDK or a standard cell or whatever. We just directly draw them in like Python scripts, which we transfer to GDS files and we send to our manufacturer partners, and they do them. So this is like one thing which kind of leads in there. And the other thing is that if you look how operation of these quantum machines looks like, it's basically they're still not like a real processor. So there's very few elements, and people do gates on a very few cells. And to me, it started to look like, again, so this is not a quantum processor. This is FPGA essentially, so that we create, 3, 5, 10 individual gates, and that looks very much like doing FPGAing. And the course was kind of a nice blend of, FPGA and then all the way to the silicon, and I thought it was going to be very interesting. And then I also pitched it inside of the company, because there's also like a potential integration in the future of these chips, which are not true chips in terms of they don't have logical elements, but to control all the things, people think of putting more like a control elements and logic really nearby or integrating with them, or like detection elements. But this is the future thing so far. So this is not implemented now. But yes, I kind of pitched that to my colleagues as well, and I was the first one to try. And after trying, I think like I'd probably be a bit more related to our way of doing things to take the analog course,
Hmm.
because as I understand, this is where you get more freedom to make all of the mistakes you really want, and and that's probably closer to what we are doing. But anyway, I'm super happy. It was quite interesting.
What part of the course did you enjoy the most?
I think the most joyful thing was playing with syllabus.
Okay.
The thing is that like in my university times, I didn't deal with accelerators. I dealt with solid state physics, and I was looking at like a very low level of the same transistor things and how the depletion zones in there works and the filters. And now you can draw it and do it very very direct, and it was very interesting to see how it works. I think it had like a great value for teaching students. I don't know if anyone uses that like in beginning courses in the universities.
Yeah, we're trying to get more people to use it instead of just showing a slide.
I mean,
Actually,
it's awesome demonstration, like
yeah.
bridging very fundamental solid state things which people learn like in solid state to the electronics, like how you connect them. That's very illustrative.
Did you draw anything more complicated than an inverter?
Probably not. I was drawing more simple things
Hmm.
and seeing that it still kind of works and how.
Nice. Okay. Um, what would you say was the most valuable part of the course?
Understanding how the thing work in between. So the section which is PDK, standard cells, etc. Since I didn't work with
Mm.
like digital designs, that was the area where I didn't have much background. Like I would understand how individual transistor works, but I did not expect that everything is built from the pre-standardized things. So
Mm.
let's say I was expecting probably more of what happens in the analog course, that you kind of do more things yourself rather than you do kind of building from the blocks, which probably was not the reasonable for me to expect that people will manually put some trillions of transistors or whatever. But it was just a blind spot for me, and that was something I had
Yeah.
no relation before.
Great. Um,
I also found very nice these parasitic extractions, and I was trying to find any tool where I could possibly do it with the PCBs, but I couldn't
okay.
find
Yeah.
anything.
Yeah. Yeah. Um,
I mean, free tools like in Altium you can do that, but don't use
mm.
that. So I was thinking like, is there something I can kind of bind together with a KitKat to do that? Couldn't find anything. But that would be a great tool for many people, myself included. But
I'll keep my eye out.
oh, if you find something, that would be great. You need to share it to everyone
Yeah.
in the world.
Would you recommend the course to someone else?
uh, Definitely. Like as I said originally, I was also advocating like more people need to go in there. Though I must say, I originally slightly underestimated the amount of time that people need to put in to actually do that. I think when I was explaining to other people, it was like more 20 hours of actual work. And then when I actually started to do it myself, I kind of found this typical timeline, which takes typical person about 6 months to get through, and I found it very realistic for me. So I started, in April and submitted in this submission in September,
Okay.
and that was pretty realistic. Of course, I mean I wasn't working like every day several hours on that, but I would mention to people that this is a really nice thing that if you need to go in there, be prepared that you need to invest substantial amount of time to actually complete that and take advantage of all what's in there. Even though I still think I want to return to one thing. I want to return to local hardening, not in the GitHub Actions. But since there was a strong deadline of the submission, I first raced to that. And to me, the biggest concern was whether it will work with real chip. So I spent quite some time on actually making the other chip work with the ASIC, which I needed
Tell
to.
us about what you did for your project.
The project is very simple. It's a chip which controls a demultiplexer chip. So there is a 32-channel demultiplexer from analog devices, and you have a 5-bit bus in there to which you submit the address which you want to be connected to the input-output, and then it switches what is connected to the output. Then you also need to get some readme signal, so you don't need to send clock to that chip, but you need to notify that the new setting needs to be read. And the motivation came again from our chips, which we have in there. So there is like about 100 of uh, electrodes which we need to control in that trap. And I was expecting that we will have 100 pins coming from our board. Then it's mounted in the cryostat at low temperature, so we have multiple stages where things are plugged in and out, in and out, in and out. And I wanted to build something to basically check the connections are correct, so that I would connect ends in board, and then something will switch them one by one and light LED on the input and on the output. And that would be the function of it. So basically checking that 4 stages of connections on multi-pin wires will be working correctly and not cross-wired, which will be a little bit of a disaster. And that was the motivation. So then that was this very simple project, which controls this external chip. And then I just wanted to make sure it actually works with that third-party chip. So I got the chip, I got a printed board, made it's a breakout board for it because it was supplied without breakboards. Then made a FPGA mockup to run the same Verilog, and just made sure that it blinks the 2 LEDs with like a human readable frequency. So it's a frequency divider from 10 megahertz to like 1 hertz, so that they can control that. I'm trying to stimulate the pin number 1, and at the end of my cable assembly, I actually get pin number 1, not 17. And since I'm not ninja, I would need like a second to make sure that the LED 1 corresponds to LED 1. That's why the long divisions in there, which was a little bit of a problem for simulations. Like I need to run it for a really long time.
Yeah.
When I finally did it for like intermediate steps, I was dividing it like factor of 100. But for the final submission, it was taking a while. The course helped me to understand how digital designs are produced in industry.
Okay. Because of the course, I was able to.
Because of the course, I was able to produce my own digital design. First time.
After finishing the course.
After finishing the course, I'm thinking maybe I should take the analog course.
You get 25% off.
Oh, they're great. Even though it was paid by company.
Oh, yeah, well, your company can take the savings and put it towards somebody else taking the course. One thing that surprised me was
One thing that surprised me was how multiple tools were integrated with each other. I mean, how things go from one to another, and we get extraction of parasitics, schematics, and tools which to me look kind of, let's say, very mature, maybe let's say from the 80s, are still doing decent job and capable of dealing with bulky projects and etc. So they're still relevant. That was nice. And to me, a little bit surprising that decent modern pipelines can be still built using something which has been around for decades.
Yeah. Great. So, any last thoughts you want to share?
Oh, if you're interested in electronics, take this course. I mean, it's an amazing course.
That's the one I'll slice out.
Well, there's nothing wrong with that. I mean, that's exactly what I meant.
Yeah. Okay. Well, thanks very much, Andrey. Really appreciate you taking the time to share your thoughts